Good morning, everyone. Thank you for joining us today. In our last deep dive, we talked all about the AI risk landscape. Well, a huge piece of that puzzle is the black box problem, the fact that we often don't know why an AI makes the decisions it does. Today, we're going to pry that box open. We're diving into Explainable AI, or XAI, to see how we can build systems that aren't just powerful, but also transparent and trustworthy. And this question, it really just hits the nail on the head, doesn't it? I mean, we're way past the point of just taking an AI's word for it. We're in an era where we demand to see the receipts, to understand the reasoning behind the conclusion. So how do we build that trust? How do we ensure accountability? Well, that's exactly where the field of explainable AI comes in. All right, so here's our game plan for today. We'll kick things off with why we even need this stuff in the first place. Then we'll get into the nitty-gritty, the actual tools in the XAI toolkit. From there, we'll see how that connects to the huge topics of justice and fairness, check out some real-world applications, and then we'll bring it all home. Let's get started. Okay, so let's dive right in. Why do we really need to look inside the box? Honestly, this isn't some abstract academic debate anymore. Think about it. We have AI systems influencing everything from medical diagnoses to whether you get a loan. And in those high-stakes situations, a simple "because the computer said so" just doesn't cut it. Not even close. The demand for XAI is real, and it's coming at us from all sides. So who exactly is knocking on the door demanding these answers? Well, it's not just one group. It turns out there are four major forces, or imperatives, that are really driving this push for explainable AI. Let's break them down. And this isn't just theory, right? It's all about practical, real-world needs. For the engineers in the trenches, XAI is their #1 debugging tool. For lawyers, it's about staying on the right side of regulations like GDPR with its right to explanation. For the actual users, like a doctor who needs to trust an AI's diagnosis, they have to understand the why to trust the what. And maybe most importantly, for ethicists, XAI is the flashlight we use to find and fight hidden bias. Let's double-click on that first one, the engineer's mandate. Let's put aside the legal or ethical stuff for just a second. Why do the folks actually building these models care so much? Because, and this is huge, XAI can catch a model that's getting the right answers for all the wrong reasons. This is one of my all-time favorite examples. It's a classic in the field. A team builds this amazing model to tell the difference between a wolf and a husky, and it's crushing it, near perfect accuracy. They're ready to celebrate. But then they decide to run an XAI tool on it just to see what's going on under the hood. And what they find is wild. The model wasn't looking at the animal's fur or ears or snouts. Nope. It had figured out that in their training data, every single picture of a wolf just happened to have snow in the background. It hadn't built a wolf detector. It had built a snow detector. Without XAI, that fatal flaw goes undetected, and you can just imagine the disaster. So now we're all on the same page about why this is so critical. Let's get to the fun part, the how. We're going to open up the XAI toolkit and look at the actual techniques engineers use to crack open that black box and ask, okay, model, why did you do that? All right, first thing to know is that there are kind of two big families of approaches here. On one hand, you have simple models. Think of a basic decision tree. They're intrinsically interpretable, meaning you can just look at them and see the logic, super transparent. The catch? They're often just not powerful enough for the really complex problems. That's where the second family, post hoc methods, comes in. These are the tools you use for the big, beefy black box models. They work after the model is trained, kind of like an investigator arriving on a scene to piece together what happened. Let's check out two of the heavy hitters. First up is a tool called LIME. And yes, that stands for Local Interpretable Model Agnostic Explanations. It's a really clever and honestly pretty intuitive way to get an answer for one specific decision at a time. So how does LIME work? It's actually pretty smart. It knows the entire global model is way too complex to understand all at once. So it doesn't even try. Instead, it just focuses on one single prediction. Let's say, why was this one email flagged as spam? LIME takes that email, makes hundreds of tiny little variations, like removing a word here, tweaking a phrase there, and it watches how each little change affects the spam score. It's basically just poking and prodding the model's behavior right around that one email. Then it fits a super simple, easy-to-read model to explain just that local behavior. The result is a clear answer, like, hey, for this email, the model really keyed in on the words free and urgent. Now, LIME is fantastic for those quick case-by-case explanations, but it is an approximation. If you need something with a more solid mathematical backbone, something that can give you both the local and the big picture, then you're going to want to look at SHAP. SHAP, which stands for Shapely Additive Explanations, is built on this really cool concept from game theory called Shapley values. The whole point of Shapley values is to find a provably fair way to divvy up credit among a team. So imagine a basketball team scores a point. Who gets the credit? The shooter, the person who made the pass, the one who set the screen? SHAP does exactly that for an AI model's features. It precisely calculates the contribution of every single input, like age, income, zip code, to the final prediction. It's that mathematical rigor that has really made SHAP a go-to standard in the field. So, just to put a pin in it, think of LIME as your expert witness. It comes in, looks at one specific case, and gives you a quick, intuitive explanation. SHAP, on the other hand, is like the full game film analysis. It uses game theory to precisely credit every single player or feature for their contribution, giving you both that single case view and the overall team strategy. Okay, so these tools are amazing, right? But XAI isn't just some cool technical trick for engineers. It's the critical bridge that takes us from understanding how a model works to tackling one of the biggest, most important challenges in AI today, fairness and algorithmic bias. So how do we actually make that leap from explanation to justice? Well, an XAI tool might tell you, hey, this loan model is paying a lot of attention to an applicant's zip code. That's the explanation. The next step is to ask the justice question. Is using zip code creating an unfair outcome for certain groups? And that is exactly what a fairness audit is designed to find out. You can think of a fairness audit as a mandatory stress test for ethics. It's something you do before a model ever sees the light of day. You test the model against a whole bunch of statistical fairness metrics, specifically looking at how its performance and, just as importantly, its error rates differ across demographic groups. If you find significant disparities, boom, that's a red flag. The model gets sent back to the drawing board for remediation. It's an absolutely essential part of any responsible AI workflow. But this is where things get really, really tricky. Because what does fair actually mean in a mathematical sense? We can't just plug the word fairness into our code. It turns out there isn't just one single definition of fairness. There are over 20 different statistical definitions. And the really tough part? Many of them are mathematically mutually exclusive. If you make your model more fair according to one definition, you might actually make it less fair according to another. Let's just look at 3 common ones to see what I mean. Demographic parity says a hiring model should select the same percentage of applicants from different groups. Sounds fair. But what about equal opportunity? That focuses on fairness for qualified candidates, making sure the model identifies true positives at the same rate for each group. Equalized odds is even stricter, requiring both true positive and false positive rates to be equal. You see the problem? Choosing the right metric is a critical, context-dependent decision, not just a technical one. All right, we've covered the why, the what, and the how. Now let's talk about the who. Who's actually using this stuff out there in the real world? Because this has moved way beyond the research lab. We're talking real tools and major government-funded programs. A fantastic example of XAI in action is Google's What If tool. The whole idea behind it was to democratize this stuff, to take these powerful interrogation tools out of the hands of only expert data scientists and give them to product managers, designers, and ethicists, so more people can kick the tires on a model. What's so cool about the What If tool is that it's completely interactive. You can literally pull up a single prediction, say a loan application that was denied, and start playing with the inputs. You can ask, what if their income were $10,000 higher? Click, and you see the outcome change instantly. You can also, with a single click, compare how the model performs for different subgroups of people, making it a powerful way to visually diagnose potential fairness problems. Now, commercial tools like Google's are amazing for making XAI accessible, but a lot of the hardcore foundational research that makes them possible, that came from a very different place. A huge amount of the momentum in this field came from a major initiative run by DARPA, the U.S. Defense Advanced Research Projects Agency. Back in 2017, DARPA poured millions and millions of dollars into solving this black box problem. And when an agency like DARPA puts that kind of money on the table, it does more than just fund a few research projects. It creates a massive gravitational pull that sets the agenda for the entire academic world for years to come. And their motivation was crystal clear. In a high-stakes national security situation, an AI's recommendation can't just come out of an opaque box. For an intelligence analyst or a military commander to trust and act on AI-driven advice, they absolutely must understand the why behind it. And that mission-critical need was the rocket fuel that really propelled the whole field of XAI forward. So as we start to bring this all together, I think one thing is perfectly clear. Explainability is not just some optional, nice-to-have feature anymore. It is an essential, non-negotiable component for building any AI system that is going to be robust, fair, and ultimately trustworthy. So after all that, the imperatives, the cool tools, the real-world applications, what's the one big idea I want you to walk away with today? This is it. Trustworthy AI simply cannot be a black box. The era of blindly accepting opaque algorithms is coming to an end. XAI is the set of tools and principles that make artificial intelligence accountable and transparent, not just to its users, but to society as a whole. It's how we build an AI future that we can not only use, but also understand. We've seen today that the drive for explainability comes from all angles, from engineers who need to debug their code, to lawyers who need to comply with regulations, to all of us who need to trust these systems. We've explored powerful tools like LIME and SHAP that let us peek inside the box. And we've seen how these tools are absolutely critical for the practical, essential work of auditing our models for fairness. I hope you'll join us for our next deep dive, where we'll be exploring the AI battlefield, defending against adversarial attacks. It's going to be a good one. Thank you so much for joining us today. For more deep dives into the technologies that are shaping our world, please make sure you subscribe to our channel, Tech, AI, and Beyond.